This video is going to talk about geometric series, both finite and infinite. So I want to start by talking about the formulas for each of these kinds of series. So first, the finite formula is S sub n, which is saying the sum up through the nth term, sometimes called the nth partial sum, is equal to a sub 1, which is the first term, times 1 minus r to the n. N is whatever this number is. So if I ask you to find the sum of the first 10 terms, you would put in 10 for n, over 1 minus r. So in both the numerator and the denominator, you see r, which is the common ratio, which is how you're getting from term to term. So if you have something written in sigma notation, you can figure out the common ratio a certain way versus when you have a list of numbers. So I'm going to show you both examples in this video. Okay. An infinite geometric series is a little bit of a simpler equation. It's just S sub infinity equals a sub 1 over 1 minus r. A sub 1, like before, is the first term, and r is the common ratio. You can only evaluate an infinite geometric series if the common ratio is smaller than 1, as in the numbers cannot keep getting bigger and bigger. They have to get smaller and smaller. The first example of a geometric series I would like to do is a finite geometric series. So I want to find the nth partial sum, which I mentioned before, just means finding the sum up through this number, so up through the 6th term. Now I went for a pretty small number, so obviously you could just say, well, I've already got 4 of the terms. I could just find term 5 and term 6, which obviously that's an option, but I want to show you how to actually use these formulas. So we are trying to evaluate S sub 6. Okay, so the sum up through the 6th term. All right, a sub 1 is the first term, which is 36, times 1 minus, now look at your list of terms and figure out how you're getting from term to term. How did I get from 36 to 6? And how did I get from 6? Whoops, I made a mistake in this problem. I would have to have 1 in here at some point. So there we go. So now I have the first 5 terms, which made this problem even easier, but I'm still going to keep using the formula. So how did I get from 36 to 6, and how did I get from 6 to 1, and how did I get from 1 to 1/6, and 1/6 to 1/36? Hopefully you guys figured out, oh, the common ratio is 1/6. Okay, so I'm putting that in there for the common ratio, and then I have to put to the nth, so to the 6th, and this is all going to be 1 over 1 minus the common ratio, which is 1/6. All right, so now we can just work on simplifying this. So there's everything getting plugged into this formula, and that's part of the battle. Okay, so now let's leave 36 on the outside, and let's evaluate 1 minus 1/6. That's in the denominator. So keep in mind, 1 is 6 over 6. So 6 over 6 minus 1/6 is 5/6. Okay. For the numerator, you can get out the calculator for that. You have to do 1/6 to the 6th. 6 to the 6th is 46,656. So we've got 1 minus 1 over 46,656. Okay? And keep in mind, just like what we did in the numerator where we made this one 6 over 6, this one is going to be 46,656 over itself. Okay, so if we subtract that over itself minus one single one, we would have 46,655, because we're subtracting 1, over 46,656. But it would be yeah, that's right, over 5/6. And then this is all still times 36 at the front. I'll put that 36 somewhere. Sorry, my work's getting a little sloppy. Okay, so now time to simplify this. So we basically have 36 times 46,655 over 46,656 times, because this is divided by, so let's multiply by the reciprocal, 6/5. And all of this as a fraction is 9,331 over 216 when you simplify it. So obviously if you put all this into your calculator, I know I did very minimal things on the calculator. If you had typed all of this into your calculator, the calculator would have given you a decimal answer, which would have been 43.19907, etc. And if you did MathFrac, there's a good chance that it would give you this. If it didn't give you this, because sometimes there's like an information overflow, you would have to resort to doing what I did with very minimal calculator use. So that's it for the nth partial sum of this problem here, 36 plus 6 plus 1 plus 1/6 plus 1/36. So now, instead of doing an nth partial sum, I'm going to demonstrate going a little bit further and doing an infinite sum, which is much less work than doing a partial sum. So there's my problem again, the infinite series. And all you need to do an infinite series is a sub 1 over 1 minus r. Okay, so we know that a sub 1 is 36, and we know that the common ratio from what we did earlier is 1/6, how I'm getting from term to term. So all we have to do is plug those things into this. 36 divided by 1 minus r, which is 1/6. So we've got 36 over, remember 1 would be the equivalent of 6/6, so 6/6 minus 1/6 is 5/6. And then dividing by a fraction, we can multiply by its reciprocal, so 6 over 5. So our final answer, 36 times 6 is 216 over 5. There is our infinite geometric series. And 216 over 5 is 43.2. So remember I told you that the decimal approximation for the first part, for the finite geometric series that we did, was 43.199. It had some more numbers after it. And the infinite series is approximately, well actually is, not approximately, 43.2. So we were already very close. We were super close to this because the numbers were already at this point at 1/36, very tiny. So as we continued on, when the common ratio was 1/6, a very tiny common ratio, the next term would have been 1/216th, which is basically adding nothing to it. So there's both of those, a finite geometric series and an infinite geometric series with the same set of numbers. So the next example that I wanted to do was number 5A from your day 2 homework, which is clearly a geometric series because we're getting from term to term. Notice that the denominator isn't changing, it's 4 all the time. But the numerator, to get from 1 to 2, we had to multiply by 2. To get from 2 to 2 squared, we had to multiply by 2. To get from 2 squared to 2 cubed, we had to multiply by 2. So we can see that this is a geometric series because we have a common ratio, which is 2. Okay, and we can also see that this is finite. So if this had been infinite, it would have ended with a ... But instead, it says, you've got all these numbers, plus, and then this general rule. And this is kind of a strange problem because we end with a general rule instead of with an actual number. It doesn't say 2 to the 20th. It just says 2 to the n minus 1. So basically, yes, this is a finite series, but all we're doing is we're getting a general formula for S sub n. We don't know what n is, but what this will allow you to do is later evaluate the nth partial sum given any n value. Okay, so we're just coming up with a general formula for this. So keep in mind that S sub n is a sub 1 times 1 minus r, which we already know is 2, to the n over 1 minus r. And if we knew n, like in the first example I did, we would put n in. But since we don't know n, we're going to leave it because we just want a general formula. Okay, so let's start plugging in things that we do know. So we know that a sub 1 is 1/4. And we know 1 minus 2, because r is 2, to the n, over 1 minus 2. And then let's just try to clean this up a little bit. So we know that 1 minus 2 is negative 1. So we've got 1 minus 2 to the n divided by negative 1. Well, let's just take that negative 1 and put a negative on the front. So all we're doing is kind of simplifying this. So negative 1/4 times 1 minus 2 to the n. There's a general formula for finding the nth partial sum. And then I think the next question actually says to find the sum when you have an actual n value. So there you would just put in n equals whatever they ask you to find. So this next example is example 5b from the homework. And this is a similar concept to the last one that we did, where you're finding a general formula. However, it's in a different notation. Instead of seeing a list of numbers added up, we instead see this one in sigma notation. So basically, sigma notation just says you're going to count up from 1, 2, 3, 4, 5, 6, etc. until you hit this stopping point. But since we have a vague stopping point, it's just the general n, you're just going to write a general formula. So keep in mind, S sub n equals a sub 1 times 1 minus r to the n over 1 minus r. Okay, so when things are in sigma notation and you don't just have a list of numbers, it's a little bit harder to figure out what a sub 1 is and what r is. Okay, so I would say the easiest thing to do is to write the first few terms. We already know that we're counting up from k equals 1 by 1. So k equals 1, k equals 2, k equals 3. Just do the first few terms to figure out how you're getting from term to term. So if we plug in k equals 1 into this formula, 2/3 to the k, 2/3 to the 1 is just 2/3. Okay, if we plug in k equals 2, we get 4/9. If we plug in k equals 3, 2 to the third is 8. 3 to the third is 27. And at this point, hopefully you can see how you're getting from term to term. The numerator is changing, you're multiplying by 2 on top, and the denominator is changing, you're multiplying by 3 on bottom. Do you see that this, the base of the exponent, 2/3, is the common ratio? That will always be the case. So that's just kind of a cool thing to know. The base of the exponent will always be your common ratio. So r is 2/3. Okay, and now we can also see what a sub 1 is. It's whatever you get when you plug in the lower bound. So k equals 1. When you do 2/3 to the 1, you've got your first value. So now we have everything we need to actually evaluate this. So we know S sub n, remember general formula because they didn't actually give us an n value, equals a sub 1, which is 2/3, times 1 minus 2/3 to the n, general formula, over 1 minus 2/3. And 1 minus 2/3 is 3/3 minus 2/3, which is 2/3. Again, I'm trying to do minimal calculator work here. Can you use calculator? Absolutely. But keep in mind, the more dramatically you write this, the easier it's going to be for your brain to deal with. Like make nice big parentheses. Make your fractions tiny, but make your whole numbers big enough that it's clear what you're adding and subtracting. Okay, so notice the 2/3 here and the 2/3 here, those can cancel. So now we just have our general formula. Whoops, except that doesn't actually cancel because that's not 2/3. Back up. Okay, this 1 minus 2/3, hopefully you were like, Miss Yolsman, that's not good. 1/3. But what we can do is we can simplify the 2/3 and the 1/3 by simply leaving a 2 out there. So our final answer is 2 times 1 minus 2/3 to the n. And now if you had an n, let's say I said find the sum up through the 20th term, you would put in 20 for that n value. So this is just a general formula. So this is my last example, and this is an infinite geometric series, and I know that because of the plus ... Okay, so it's not finite. However, if it were finite, it would not have the plus ... it would just end. Okay, so we're adding up these numbers. They go on forever. This is okay because the numbers keep getting smaller and smaller. So to do an infinite series, we just need a sub 1 over 1 minus r. We can see that a sub 1 is 2. But what is r? How am I getting from term to term? How did 2 turn into negative 1/2? And how did negative 1/2, this might be easier for you to see, turn into positive 1/8? And how did positive 1/8 turn into negative 1/32? Okay, so hopefully you're noticing, oh, those are alternating in signs, so r definitely needs to be negative something. How does 2 become a half? How does a half become an eighth? So let's focus on the 2 becoming an 8, the 8 becoming a 32. So clearly it was multiplied by 1/4. The denominator is changing while the numerator isn't. Okay, so now we have everything that we need. We have a sub 1 and we have the common ratio, and that's it. So you're just plugging in and simplifying. So a sub 1 is 2 over 1 minus r, which is negative 1/4. That would be 2 over, keep in mind that this double negative here, 1 minus negative 1/4 would be 1 plus 1/4, which is 5/4, because that's 4/4 plus 1/4. And then multiply by the reciprocal, so 2 times 4 over 5. So our final answer is 8/5. I ran out of room, so I'll write it over here, 8/5. So your final answer will tend to be kind of a weird fractional number. Sometimes you luck out and you get a whole number. But that's about it for infinite and finite geometric series. Hopefully this shines a little bit of light on the confusing homework problems and some of the lingo and what to plug into these formulas. So thanks for your homework questions. Hope this video helped.